So now let's take a look at our nitrogenous bases and draw those. We'll start by describing the two different types. We have the pyrimidines and these are six-membered heterocyclic aromatic rings containing two nitrogen atoms. Oops. So we're going to have two nitrogen atoms in them. This is a long name, but only one ring. At least that's how I used to try to keep them what do I want to say? Keep them straight, I guess, is what I was trying to say. And we have a C, double bond C here, and then a single bond here. So, this is planar and relatively insoluble in water. The numbering system starts with the nitrogen atom at the bottom of the ring and proceeds to the left. The other basic nitrogenous base is a class called the purine ring, or the pyrimidine ring up here. There are two rings of atoms. One ring resembles the pyrimidine ring, and the other the imidazole ring. And you have seen a variation of that in nucleic acids. So there are 9 atoms in this fused ring. And this is slightly puckered at the interface, or the fusion. So I'll say fusion point. Short name, big structure, 2 rings. Okay. So we have carbon, single bond to carbon. This is the fusion point. There's my nitrogen. Got a nitrogen down here. And, oops, carbon double bonded to that nitrogen. And then nitrogen, nitrogen, double bond C, single bond. Numbering here, and there's a hydrogen here attached to this particular nitrogen. Numbering here begins with this nitrogen, goes around this ring till we get to the top, then we jump over to the nitrogen in the imidazole ring, and down to the last nitrogen, which is the 9th atom. So our structures that are components of RNA and DNA, are going to be derivatives of these two types of nitrogenous bases. So we're going to look at those derivatives, or the pyrimidine bases first, and those are cytosine, uracil, and thymine. So cytosine is present in both DNA and RNA. Uracil, only RNA, and thymine only DNA. So these are, thymine is the corresponding base in DNA, and it is converted, or it is substituted with uracil in RNA. Okay. So cytosine and I'm not going to use blue for those nitrogens this time around. I'm just going to use a different color for the functional groups that are present. Again, that numbering starts the bottom in the nitrogen ring, and 2, 3, 4, 5, 6. And so when we name this, and this might be more helpful to learn the names, then you can easily draw the structures. And this would be named, or is named, 2-oxy 4-amino I went the wrong way around the ring. 2, 3, 4, 5, 6. You know, I drew it backwards in this one, or I flipped it from my original drawing. Sorry about that. So then I numbered wrong. 2-oxy 4-amino pyrimidine. Watch that next time. Okay, uracil. Here's my black one. So again, our we still have a carbonyl in that true position, and I should some hydrogen here. This is the site of sugar attachment. I meant to note that, which we will also be doing. So, sugar. The difference between uracil and cytosine is in the 4 position, where we change that amino group to another carbonyl group. So this is named 2-oxy 4-oxy pyrimidine. And of course, I'm not drawing in all the H's, but there are other H's here. Thymine Oops. We still have that carbonyl in the 2 position, carbonyl in the 4 position, and I jumped the gun here. We have a methyl group in the 5th position. So 1, 2, 3, 4, 5, 6. So this is 2-oxy, 4-oxy, 5-methyl pyrimidine. So now we're going to look at the common purine bases. Which are adenine and guanine. Adenine is also called 6-aminopurine, and guanine is 2-amino 6-oxypurine. And again, it might be helpful to just memorize the basic structure of the base and then the name, so you remember where these substituent groups are located. So, sorry, got a little goofy. And this is and for these, this is the site of the sugar attachment. And we have, whoops, I goofed there. This is a carbon. Carbon, and oh, I didn't leave enough room for my amino group. Here's my amino group. Attach the carbon at the top of this ring. Sorry about that. Everything else is good there. Okay, so 6-amino purine. And so if we draw guanine, oops, let's go back to black here. Here, and carbon. Here's our carbonyl group, and then we have an amino group here. So 2-amino, well, I did the same thing again, didn't I? 1, 2, 3, 4, 5, 6, 2-amino 6-oxypurine. Now for the 2 forms of ribose that we'll find in RNA and DNA, and actually both of these are present in DNA and RNA. Okay. These both occur or are found in the furanose form. And we have D-ribose and deoxyribose, or deoxyribose. So ribose, the deoxyribose is going to be found in DNA. The beta-D ribofuranose has this structure. Sorry, I'm not doing very well following my lines here. I purposely picked up this graph paper, and then I'm not being as careful as I had planned to be. Okay, this looks good. 1, 2, 3, 4, 5 carbons in our ribose. So this is beta-D ribofuranose. And the only difference between this molecule and the deoxyribose is that the 2 position has lost its hydroxyl group. So maybe I can do a little better job this time. Here we go. So hydroxyl here, but we only have a hydrogen in that 2 position. So this is beta-D 2 ribofuranose. Squeeze that in there. Okay, so we've covered the basics here, basic components that come together to form a nucleoside, and so that's what we're going to draw next. Nucleoside, well actually we're going to draw the nucleotides, but let's define, nucleoside, and this is a base plus a sugar that are linked via a glycosidic bond. And for us, these will be ribonucleosides because they're going to contain, well, we could have 2. We could have ribonucleosides, which would contain ribose, or we could have deoxyribonucleosides. Which of course are going to contain, 2 deoxy D-ribose. A nucleotide, which is actually what we're going to draw next, is a nucleoside that has a phosphoric acid esterified to the sugar. So we're going to start with AMP, which is adenosine 5' monophosphate. there is ADP and ATP, adenosine diphosphate, adenosine triphosphate. So there are 3 forms of nucleotides based on the number of phosphoryl groups that are attached to them. So AMP, put that up just a bit. Make sure I make enough room for my base up there. So it's through that 5th carbon that we have the attachment of that PO3 group, and this is negatively charged. So we have 2 negative charges on this molecule. Make that a little longer. And here's the point of, oops, that's an N, sorry. Just I caught that one quicker. Double bond here. Got a little long there. And the amino group here, double bond, double bond, double bond. Looks good. Okay. So this is AMP, adenosine 5' monophosphate. And again, that 5' coming from this 5th carbon in that ribofuranose ring. I don't think I fit GMP there. Let's look at GMP, or guanosine 5' monophosphate. Whoops. There's the uneven spot here. So again, the only thing that's going to differ is the identity of the base that is attached to that sugar that has the esterified phosphoric substituent group on it. So that group, again, this is going to be our linkage to our base. And through that nitrogen. Double bond. And that is guanosine. And I'm going to need another piece of paper here, graph paper. Actually, maybe I can get the smaller ones over here. So let's look at cytosine monophosphate, CMP. I'm sorry, and that's 5' as well. But here we just have our pyrimidine bases attached. Again, same linkage. Through that, whoops, I shouldn't have gone up that high. The nitrogen at the base of that ring. this is, sorry, I really kind of didn't leave enough room. We've got a double bond here, and then we have an amino group here. So cytosine 5' monophosphate, and the last one is UMP, or uridine 5' monophosphate. We'll start lower. Oops. And then we have the two carboxyl groups in uridine. So now let's take a look at the structure of an oligonucleotide, which, if asked, you should be able to draw. So essentially, this is just a polymerization of our nucleotides, a polymer of nucleotides. Okay. And these are linked via phosphodiester bonds. Okay. They are always written in the 5' to 3' direction, or drawn in that direction. I'm just going to draw generic ones for you, but if I should ask you to draw, the linkage of, let's say, adenine, guanine, cytosine, you would need to include the actual bases. But the backbone of this, we have our phosphoryl group, and so this is the 5'. And the linkage is through the 3' hydroxyl, or the site of the 3' hydroxyl. And of course we have our base linked here. And so, I don't know why I did that. The linkage is here. That's the O from our hydroxyl group. And then, of course, our second base. And then this linkage just continues to go in that angled direction. I'm going to go over, just discuss the DNA double helix that's created by the AT and GC specific base pairing. Then we'll draw those base pairs. You should be able to do that for me. So I'm going to Oops. So the DNA double helix is basically two, I should double helix. Two polynucleotide strands that run anti-parallel. To one another. So they kind of make a ladder that's twisted in the right-hand direction. So we can call this a DNA ladder. So think of this as if you climbed a helix or a spiral staircase. You would hold the outer railing of the sugar phosphate backbone with your right hand. So the outer railing is the sugar phosphate backbone. On your right. So the base pairs then are going to be centered in the middle of the helix, and they're approximately perpendicular to the helix axis. And they stack on top of one another. So the core of that helix is essentially solid. So we have the base pairing is A, base pairs with T. These two lines reflect the fact that there are two hydrogen bonds. So these are hydrogen bonds, they are not chemical bonds. So it's that intermolecular force that is holding those two together. Now, these are going to be deoxyriboses because they're in DNA. I'm not drawing the sugars, but they would be attached to deoxyribose. And if I ask you to draw the base pairing, you do not need to include the sugar, just the showing the A and the T, for example, with the hydrogen bonding between them. So a T-base pairing, let's see, let me go here. And this nitrogen, oops, I got one too many hydrogens there. I got a little long there as well. Let's see, let me go back and check something. Make sure I've got okay, yeah. What I had, I'm sorry, I'm talking to myself. I do that sometimes, so let me make sure I have that right. So this would be the sugar attachment. Or the side of the sugar attachment. Now, this nitrogen has a hydrogen. This nitrogen has a lone pair of electrons. And so for thymine, we have that carbonyl at the top. We also have that nitrogen. got a double bond there, and this nitrogen has a hydrogen attached to it. So we're going to get, and keep in mind that this oxygen has 2 lone pairs of electrons, and this hydrogen then can bond or form a hydrogen bond with that oxygen, and this hydrogen will be attracted to the lone pair of electrons on that nitrogen atom. Now, guanine and cytosine base pair, and these form 3 hydrogen bonds when they interact with one another. So again, this is the sugar attachment. Double bond here. Carbonyl, nitrogen with a hydrogen. Nitrogen here. Double bond C, and that amino group, which has 2 hydrogens. Of course, this will have lone pairs of electrons, and I'm going to have to draw this a little chipped, I think, to make this work. Amino group, my oxygen, there we go. Yeah, that's really distorted, but sorry. I do have to kind of tip that. This is the sugar attachment, or site of the sugar attachment. There is a double bond here. I didn't make that very clear. Carbonyl, this nitrogen has a lone pair of electrons. I should have drawn this one like this. So this hydrogen is going to hydrogen bond with a pair of electrons on that carbonyl group. This hydrogen is going to be attracted to the lone pair of electrons on that nitrogen atom. And finally, the hydrogen on this amino group will hydrogen bond with the other carbonyl in cytosine. And that's it. We're drawing nucleic acids and base pairs.